The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
This afternoon we have two sessions really to talk about some of the contributions of Gene Corley. Gene passed away earlier this year. Obviously is extremely well known in the industry and throughout the profession, and as we talked about it, and this session was primarily has come out of ACI Committee 318, the building code, and as a number of us talked about what might be done in a session for Gene, we started to talk about the areas where he was his contributions were known, where he had made significant contributions, and it really is wide-ranging. So what we have decided to do was to break up the sessions in a few topic areas. This morning, or this afternoon, this first session, we'll be talking primarily about some of the research that Gene was involved with and his contributions in those areas of research. We're fortunate to have speakers who have worked with Gene over the years and who have been involved in a number of these projects. And our first speaker is Neil Hawkins, and Neil is an emeritus professor at the University of Illinois, now retired. But he's going to talk about the work on analysis of flat plate and frame construction. That was actually some of, I would say, some of Gene's earliest work in the research area. And so, Neil, I'll turn it over.
Thank you, Tony.
Do you want to use?
How about this one?
Okay.
Everybody hear me? Okay. Thank you, Tony. Tony, when he was introducing us, was going to say that he's going to only give our name, rank, and serial number. So I'll give you my serial number, which is 2/7163889. And that's very appropriate because on Wednesday nights for the second year of our job as graduate students under Meta and Chet at the University of Illinois, Gene and I used to go down to the Armory in Champaign and go through Army Reserve training sessions. And I had to wear my funny costume because I was an Australian, and Gene would wear his US Army ROTC costume. So anyway, here where I'm going to talk about flat plate and flat slab construction and Gene's contributions to this in particular. And what I'm going to break it down into is two parts. First, what he did on the equivalent frame analysis, and secondly, what he did on the testing of analysis of flat plate and flat slab systems shear strengths. Now, in the equivalent frame analysis, if you want to go and read it, which I actually did for these presentations, and it becomes very interesting when you read it because you start to see a chronology of how somebody's thinking on these things has developed. So the first publication from Gene in this area of equivalent frame analysis was Structural Research Series number 218 from the University of Illinois, which he acknowledges his advisor was Chet Cease and his whipmaster was Meta Sozen. So that thesis you can download from the University of Illinois' website and you can look at it. The second one he did with Jim Jerza, who is the second speaker, the ACI Journal in November 1970. And then he wrote a very interesting paper, which I didn't read till I got to this session, which was Concrete International, an article on how to use the equivalent frame analysis, written in December 1983 with Dan Vanderbilt, who had again also been a student at Illinois. Based on how he started to look at slabs, he then started to think about what can we do with the way these slab systems seem to fail, which was in punching shear. So he started this, if you like, when he went to PCA and did the New York World's Fair waffle slab tests, which he did with Don Magura. And then when I went to work briefly at the Portland Cement Association, following Jim being there too, we worked on shear head reinforcement. And that was the way Gene thought about answering the punching shear problem. Then we went ahead and looked at the moment and shear transfer issue, because my job at PCA was to look at what happened with shear heads when you had moment transfer, not just the punching shear alone. And then Gene followed with looking at ductile flat plate structures to resist earthquakes, and some of the first work there which appeared in the World Conference on Earthquake Engineering. And finally he sums this all up in an article in ACI SP 59 on shear in two-way slabs, an ACI approach, when there was a discussion with what was going on between ACI and FIB. So I'll just review this. So in his early professional years, Gene was sort of free, not like the rest of us under the whip of being research assistants at Illinois. Gene was a National Science Foundation fellow, so really he had to be more guided in a way than the rest of us were. And he did that from 58 to 61. Then he got his PhD in structural engineering from Illinois in 1961, and what I remember there was he was here one day and gone the next because he had to go into the military. And he went to the U.S. Army Corps of Engineers at Fort Belvoir from 61 to 64. And then he became structural research manager of the PCA Research and Development Division in 1964, and he held that position until 1972. And so I show here two slides from the testing of the flat slab that went on at Illinois under Meta's guidance, and that sort of influenced how Gene was thinking about these things. And you can see in the lower left corner, Bill Gamble, and peering out from under the slab is Ned Burns. And then in the other one, hanging upside down, is a fellow Australian, Ken Fox, looking at the loading on the slab. So why this equivalent frame analysis? Well, it actually first came into the ACI 31871 based on Gene's PhD thesis and Jim's PhD thesis that followed. Gene looked primarily at the cases of uniform loading. So what he did in his thesis was sort of revised by what followed in Jim, who looked at pattern loadings. And so therefore they came up with what went into the code. Now the early ACI codes just had the empirical method of design, which we still carry over to this day. And it was restricted to slabs with certain properties, the span to depth ratios and sizes and so on. So to overcome this, the 1941 ACI code introduced an elastic design method, giving similar results to the empirical method for the loaded test floors, that's the floors back in the 1900s, for slabs with dissimilar properties. Well, when that method was sort of introduced through the California Building Code, and you just divided the slab up into frames and you worked with those frames. But really what was figured out was that wasn't the way the frame actually worked, because in the bottom slides you get what is the way the actual structure deforms by the method of the 41 ACI code versus the method that Gene thought it should deform in the upper code, upper part of the slide. And so the 1971 code introduced a number of concepts. The first one was a varying slab stiffness, and of course, how many of you remember Hardy Cross's method of analysis? Yeah, everybody. I think we're all old enough to remember Hardy Cross's method of analysis. Well, that's what the equivalent frame is based around. I mean, it's based in trying to give you answers to Hardy-Cross's method of analysis. So you need to answer, first of all, what's the 1 over EI diagram? So it came up as shown on the left with ways of dividing the structure up so you could come up with the 1 over EI values as you went across the width of the structure in the direction of the frame. And then there was simplified physical methods for illustrating the intent of how you did the connection to the exterior of the frame. And this is where things really sort of are more difficult to deal with. It's easier to deal with the interior of the frame than it is to deal with the edge of the frame. So in the right-hand diagram, in the upper left, then we have what you have to do with what is meant by a monolithic wall, and then what you have to do when you've got a spandrel beam, and what you have to do when you've got a column only in terms of what's the equivalent frame you're trying to deal with. And really, the major issue in here was how did you deal with that torsional effect of the slab passing the column. And so going back to how did I go from the bottom diagram, which was what the 41 code was dealing with, to the hammerhead of what the 71 code was dealing with. And so we talk about then the width of that section. We talk about the distribution of the unit twisting moment along there. We talk about the twisting diagram that results, and then we talk about the unit rotation results. And we can talk about, therefore, the torsional stiffness and the C factor in the torsional stiffness. In Gene's thesis, the unit twisting moment, so figure 3b there, was uniform over the length L2. And with Jim's thesis, that was modified to show the patterns which are down there on the left slide. So for the equivalent frame then to connect into this slab, for which I'd shown the 1 over EI stiffnesses, then you had to get this flexibility for the column, and you got the equivalent column then, which was the flexibility of the real column plus the flexibility of the actual torsional members framing into the column. So then, how good was this? So here is the layout on the left of the 9-panel reinforced concrete flat plate, which was dealt with at Illinois, and you can see that on one side of the structure there was a deep beam, maybe you can see that, and on the other side there was a shallow beam. But on, correct me if I'm wrong, Meta, but on every side there was a spandrel beam. And one of the things that sort of is a bit different is that we apply it in the code to structures without spandrel beams now. But anyway, in Gene's thesis he compared the measured and the computed service load moments in here, and you can walk all the way across the structure from the shallow beam to the deep beam, and you can see how you got the moments measured from strains, the moments measured from the reactions. He got the moments determined by a difference solution. He got them by the proposed frame analysis, and then he got them by the ACI code frame analysis. And you can immediately see a big differences there in the spandrel beam values, and then the ACI code empirical moments. So that was the basis in Gene's thesis. And then after that we got the PCA 3/4 scale tests. So they took the flat plate structure that had been tested at Illinois and built one in the PCA lab at 3/4 scale. And this was before Gene actually went to PCA. He came in shortly after that, but he wasn't, to my best of my knowledge, involved in doing any of this testing. And so we can see again, looking across, a comparison of measured with computed moments, and we see the calculated uniform load moment, and then the calculated maximum design moment, so that's to take into account pattern loadings, and then the ratio of the maximum to the uniform load moment. And so we go down and we find that there's actually very good agreement with between the PCA three-quarter scale tests and the University of Illinois quarter scale tests. The 83 paper is very interesting because it talks about equivalent frame procedure limitations. And the first thing is that the method assumes analysis by moment distribution methods. So I scratch my head a bit and wonder why we still have that in the code. But it's the method. The method was calibrated then for gravity loadings only, because that's what it was done, by comparison to the URVI quarter scale tests and the PCA three-quarter scale tests. The method was based on the stiffness of uncracked sections. The method was not calibrated for lateral loadings, but theoretical studies that Dan and Jean did suggested a cracked section stiffness equal to 1/3 of the uncracked section stiffness. And we refer to that currently in the code in 13.5.1.2. And I can remember a number of discussions with Jean about, well, why don't we say something in the code itself? Why do we only put it in the commentary? How do we come up with this cracked section stiffness? All right, the method is still used extensively, and as in the code, it remains essentially unchanged since 1971. So there's significant contribution there. Then I said, all of these slabs that were tested at the U of I and the PCA were for gravity load only, and they had a 70 PSF live load and 86 PSF dead load. They were grade 40 steel, you might want to note that, and 3,000 PSI concrete. Both slabs failed by punching at an interior column. The strains in the top steel of the column were greater than 7 times the yield strain at punching. The failure load was 369 PSF, but was only 85% of the ACI 4 root F prime C value. In other words, we wouldn't have predicted this punching shear. Well, you could say, well, the slabs were failing in flexure, therefore it was logical to do punching shear, but if you wanted to keep on going to the full flexural capacity, the computed yield line capacity was 350 psi, but if you were really wanting to get something that didn't collapse by punching, then you would have to go to a larger load, probably in the 369 psf at which they punch. So punching was classified as a secondary failure due to the extensive yielding of the reinforcement around the column prior to failure. So the issue became really how to prevent the punching shear failure. And I think this becomes very relevant when we start to think about blast loadings and earthquake loadings and other things, because we're asking for more ductility than the ductility that was obtained in those tests. So the question becomes how to evaluate the punching shear strength, also when there is moment being transferred from slab to column. And then under Jean's leadership, the PCA set out to make significant contributions to addressing both those issues. So in the 1960s then, the early 1960s, the original Wheeler patent for a shear head had just come out of being patented. Now Wheeler didn't let people go around using these shear heads, so much of the structures that were built didn't really use it. They were used sometimes, but Jean saw an opportunity for this to be more widely used. So he took the typical interior slab specimen, shot it up on a column, put a shear head in between the top and bottom reinforcement. And I show a couple of shear heads out there, and you notice all the wires coming off the top shear head. That was where they were instrumented with strain gauges, And they turned out to be very important to being able to understand the actual loading being felt by the shear head itself. Thank you. Maybe I won't cough so much. So I show here from the original paper, we tested 10 specimens with shear heads. I didn't. I think you did, Jim. You did some of them. Sarusha, well, didn't you develop the program, the ideas? Well, that's what Gene says in one of his papers. And I know the other person who did the actual testing on this was Sarusha. But the thing that we found was that the shear head increased the shear capacity in the same way as a larger column. But for warning of the failure, the shear head had to yield before the punching occurred. And when that happened, then the critical section for shear did not extend to the end of the shear head. So if the shear head was what we classified as over-reinforcing, and that would be what you would get in a lift slab or a short shear head, it punched around the end of the shear head. But if you got the right capacity in the shear head, and the shear head started to yield near the column before the punching occurred, then the critical section where the punching occurred came inside the end of the shear head. So that was drawn up in the code, and we got it from actual instrumentation, where I show you the results there from the strain gauges from which we determined the actual shear, and then we idealized it as shown down there. We talked about then a K factor in there, which was the EI of the shear head to the EI of the composite section of width C plus D, so the diameter, the side dimension of the column plus the effective depth of the slab, so that's the punching shear for a slab without a shear head. And we said that K had to be equal to or greater than 1.15, only because we never tested anything less than K equal to 1.5. And you then came up with a expression up the top there for the moment capacity that was required in the shear head. So we now have a moment capacity required for the shear head, and we have a critical section which we talk about for no shear head, a small shear head, and then a large shear head. And that's what the code says. But then we have to come to this issue of, all right, well, punching shear exists in most structures, but in a lot of structures now we have to talk about moment transfer. And, you know, in the exterior of a flat slab, nearly always getting moment transfer, even at the first interior column. So you have to sort of deal with, what do I do with this? So we say a fraction gamma sub f m sub u has to be transferred by flexure within lines 1.5 h either side of the column, and we define gamma sub f, and we define B1 in there as the column width C1 plus D. Now for reinforced concrete slabs and exterior columns, gamma sub f can be increased to 1, so you get rid of the moment transfer problem, provided VU does not exceed 0.75 phi VC for edge columns and 0.5 phi VC for corner columns. And this is based primarily on work that Jack did and talking about what he saw. But for interior columns, gamma sub f can be increased by 25%, but not greater than 1, provided VU is a much lower value, 0.4 phi V sub C, and the net tensile strain is equal to or greater than 0.01. That's not very much. And this was introduced, if you like, by what's the guy from New York? Jacob Grossman, is that right? So, to a large extent, you can get rid of the problem of moment transfer of an exterior column. But for an interior column, you quite often can't get rid of it. So that's the important way of looking at this. So what Jean and I sort of had hit on, and this was followed up by Dan Vanderbilt and Jean in their paper on frames, was looking at the connection as a beam analogy, in which then we would have a flexural member, looking at the left-hand diagram, a bottom, a flexural member F1 coming into the front side of the column, F2 coming into the back side of the column, torsional members T1 and T2, and to get the right response we had to have then a torsional spring, a flexural spring, and then we had a bond slip spring that came out the front, and then we could get all the rotations correctly there at the structure, and as shown in the left, we could match them up. But this just becomes very complicated to try and put into code. You can put it into a computer analysis and come out with a good result, but it's not hard to do, not easy to put into a code. But here it is as a beam analogy, moments and forces. This is what you're thinking about in the middle, and then there's a critical section for what you could say is failure by moment torsion, so it's moment on the front face and torsion on the side faces of the column, and I show you for ease a exterior column connection there. And then you can have a critical section for shear torsion. So you're actually starting to think, well, maybe I can divide up my critical sections and talk about one for moment and one for shear. And why did this come about? Well, to a certain extent, this was because of the studies that we made on exterior column connections with shear head reinforcement in them. And in that, I show you the specimens on the left, and again an instrumented column on the right. And Jim, we talk about trying to remember things. I remember that the reinforcement was grade 60 steel, but I had no idea till I read the paper again that we use sanded lightweight concrete. There's 3,000 psi in there. I'd forgotten that entirely. Anyway, so this was the test set up. Here's a nice picture of us in the PCA lab doing it. And from this we got, again, concepts of under-reinforced slab column connections with shear heads in them, over-reinforced, and over-reinforced with different lengths of projections. And if you go in here and look at the different ones, you can see quite a development of more ductility associated with the presence of a properly proportioned shear head, which I'm going to talk about as under-reinforced. So if you have an under-reinforced shear head, you can drive past the punching shear for a connection without a shear head and get quite a bit of ductility out of it, but not that great a ductility, but you do have a descending portion to the curve, which again would be of great interest to people these days. So what you ended up doing was saying, look, for the shear case, I can just look at the critical section as the same for an exterior column connection as we had for an interior column connection. But for the moment case, well, we're going to look at the shear stress due to moment transfer, the shear head was absolutely useless. So we went back and computed our shear stress for the moment transfer case for a connection as if it didn't have a shear head. And then we would add those two shear stresses together. Now, they don't occur at exactly the same place. They're about the same place. But that's what is done. And that's what continues to be done in the code. And that's what continues to be done in the code, whether we're talking about stud reinforcement or shear head reinforcement or shear stirrup reinforcement. I don't need to go into this. So what still needs to be addressed? I think the first thing we need to realize is how to deal with this punching shear problem, which limits our rotations. All right, we can get to this strength, and it starts to yield and deflect, but how does it punch here? And the answer is we really need to, in my opinion, so this is my opinion to wind this up, the critical shear stress crack theory from Newtonian, who says, look, that incline crack forms in there, and as the slab tries to deflect, you lose aggregate interlock, and that causes the punching shear. And then Garley has said, well, gee, if I just limit that shear strength to the actual general yielding around the column, then we can compute the general yielding around the column as a moment per fractional strength per unit width, and that value becomes 8m. And if we start plugging that into the results, and actually require then that the shear stress can't be greater than the fractional strength, we start to get a good answer for the limiting shear capacity. It doesn't tell us anything about rotations, but we've got to start going into that in more depth. The other thing that needs to be addressed is all of these slabs we tested were 6 inches and 7 inches deep. We build waffle slabs. We go to slabs 2 feet thick. We do all sorts of things now. And Motoni again and a number of people have started to look at slabs of greater depth. And you see, actually, there's a few results out there at 20 inches and a few results out there at 26 inches. And if you look at those and you try to talk about a size effect from fractional mechanics, then the answer is that once the slab exceeds about 9 inches in depth, you need to start to introduce another factor, which would be 3 over the square root of d to reduce your V sub c value. Finally, I think we need to deal with the issue of developing a conceptually consistent punching shear, moment transfer and ductility provisions for connections with shear reinforcement. We need to cover stirrup reinforcement, stud rail reinforcement, fortress reinforcement and shear head reinforcement and make them consistent. And talk about what the ductility is and how do we get up with this ductility. And thank you, Gene, for your contributions, which really set a lot of this off.
Thank you, Neil. We have time for a couple of questions. Are there any questions for Neil? Okay. Jack?
So, Neil, excellent presentation, and the slide you showed maybe 2 or 3 or 4 slides back on size effect.
Yeah.
Is there a serious implication for foundation maths in that slide?
Yes.
What's your opinion on that?
If I had to do it, I would use the 3 over square root of d, but never get lower than 2 root f prime c.
If there's shear reinforcement in the math, does that help things, you think?
Of course.
Okay.
I remember.
Does this effect go away or no?
No, but you'd be lowering VC, so you would be requiring more shear reinforcement.
Thank you, Neil.
Thank you.